Hello everyone, welcome to lecture 28 of the online course on modern display technologies, flat panel displays. Today's lecture will be on phase retardation LCDs and cell gap design. So here is the lecture outline. We'll talk about the phase retardation type. We'll discuss the transreflective twisted nematic or the super twisted nematic, that is STN, and the parallax problem. We'll then also talk about the transreflective mixed mode twisted nematic or MTN LCDs, and we'll show how to fix the parallax and the low reflectance problem. After that, we'll look into the patterned retarder and the mixed mode phase retardation designs. We'll compare the dual cell gap versus single cell gap in transreflective LCDs, and finally we will provide an overview of the overall performance such as color balance, image brightness, and viewing angle. So in the previous lecture we have seen that absorption, scattering, and reflection types, these are all covered, and each minimizing polarizer count to maximize the brightness, but each paying for it for the advantage with a different practical cost, something like limited contrast, high drive voltage, okay, or manufacturing complexity, right? And none of the three could achieve the widespread adoption, right? So all the designs in this phase retardation type, okay, are basically work by using an applied voltage to reorient the bulk liquid crystal director, okay, or you can say it's basically the voltage induced liquid crystal reorientation, okay. So which changes either the phase retardation the liquid crystal imparts on the light that is passing through it, okay, as in homogeneous or the vertical alignment cells, okay, or you can also see some kind of polarization rotation behavior of a twisted structure, as you can see in the twisted nematic cells. Now both effects basically originate from the same underlying voltage induced liquid crystal orientation that you have already studied, right? So in short, you can say that the mechanism here is nothing but voltage induced liquid crystal orientation, which changes the phase retardation, okay, or for the that is mainly for the homogeneous vertical alignment, okay, cells, and for the twisted nematic cells your polarization rotation state is going to change. Now what is the requirement for the two polarizer? So you have understood that because T mode and R mode must work simultaneously, okay, you generally require two polarizers, okay. So what happens, like, because a clean bright dark switch by retardation or polarization rotation fundamentally requires analyzing the light's polarization state both before and after the liquid crystal layer. So two polarizers are generally needed so that both the transmissive path, that is through the backlight, and the reflective path, that means your ambient light getting bounced off the transreflector, each can be properly analyzed and switched, okay. Now why the advantage that phase retarder bring that win in the industry? So despite the polarizer or the brightness trade-off, the states having this kind of phase retardation, okay, so there the LCDs can achieve higher contrast ratio also lower driving voltage, and they are also fully compatible with the existing high volume transmissive LCD manufacturing lines. So what happens, the commercial success is much higher for this kind of phase retardation type. Okay, so what is the scope in this lecture? Here we'll look into the transreflective twisted nematic or the super twisted nematic and the parallax problem. From there we'll talk about the mixed mode twisted nematic LCD fix for some of the problems. Okay, and then we'll talk about the patterned retarder and the mixed mode refinements. We'll compare the dual and the single cell gap engineering and also comment on the overall performance. Okay, so in this particular way the student will be able to understand the full arc of this LCD designs. So let us look into the transreflective twisted nematic LCD, the structure and the voltage of operation. So here is the structure, as you can see here in this transreflective twisted nematic LCD. Okay, there is this 90-degree twisted nematic liquid crystal cell placed between two cross polarizers. Okay, so there are substrates, and then you have this polarizer 1 which is 0 degree and the polarizer 2 which is 90 degrees. So this is basically placed between two cross polarizers, and then you have this backlight at the bottom, ambient light source on the top. Okay, so what you have, you also have a transreflector here. So the transreflector is basically laminated on the outside of the bottom polarizer. Okay, and after that you have placed the backlight. So what happens in the voltage off condition, that is basically the transmission mode. Okay, so it is basically the bright normally white mode, because the light from the bottom polarizer, okay, basically follows the liquid crystal twist and it rotates 90 degree and it could exit through the top polarizer, that is the familiar twisted nematic polarization rotation effect. Okay, now something interesting happens in the voltage off states reflective mode, that is also giving you bright, because when the light is entering from the top, okay, it is basically getting rotated by 90 degree by this twisted nematic layer. Okay, and then it passes through the bottom polarizer and gets reflected of this transreflector. Okay, so when it is getting back, on the way back it again gets rotated by further 90 degree by this liquid crystal layer again, and then they get it just like 180 degree shift, and it's like it is aligned to this polarizer 1 and it can escape. So you again get a bright state, that is from the reflection mode. So this is what we have seen for the voltage off operation. Now in the voltage on operation you are basically getting the dark state. So what happens, the bulk liquid crystal director tilt nearly perpendicular to the substrates, and the two orthogonal boundary layers basically self compensate. So the cell no longer modulates the polarization in either mode. Okay, so in both cases the light is getting blocked by the cross polarizers, so you get basically dark in both transmission mode as well as reflection mode. Okay, so here you can see that this is the transmittance and reflectance curve, and this is the applied voltage. So the dark one shows the transmission mode and the lighter curve shows the reflection mode. So you can see very well that in both cases the off states are basically overlapping. Okay, because in both cases light basically experiences the same bottom polarizer, then to the liquid crystal, then the top polarizer sequence, and they are basically 90 degree out of phase. So you actually can see that this is a very simple practical design and you are able to get no light out of it. Okay, so this is a good one, and you can see that the good steady first minima for this 90 degree twisted nematic happens at a particular cell gap size. So if you consider phi to be 90 degree, your d delta n comes out to be 476 nanometer when you are considering the green wavelength, that is lambda equals 550 nanometer, right? Now one big advantage I should point out here is that why this T mode and R mode overlap so well. Okay, so here you can see in both cases light basically experiences the same physical sequence, okay, and that gives you this structural symmetry, which makes it a good grayscale matching between the two modes. Okay, so one of the most genuine advantages that you can get. Now let us look into the parallax problem that is there in the transreflective twisted nematic LCDs. So with a careful geometric ray tracing argument, by laminating the polarizer and the transreflector on the outside of the bottom substrate, okay, you can actually see a visible double image defect, which is called the parallax. So and this particularly get worse when the pixel size changes. Okay, so this particular figure tells you this effect more clearly. So here you see that you basically have this polarizer, okay, then you have a substrate, and then you have this twisted nematic liquid crystal, then another substrate, and then a polarizer and a transreflector. Okay, so the off pixel ray paths AB, okay, and CD, okay, so these two can basically, so you can see here that produce a dark image A prime B prime. Okay, so this is on the pixel, so you can carefully see this, that A and B giving you A prime B prime. Okay, however the CD gets slightly you get a separate shadow image of C prime D prime, okay, below it, because the transreflector and the bottom polarizer are basically laminated outside the thick bottom substrate. So as you can understand, the main root cause of this problem is that the polarizer and the transreflector are laminated outside the bottom substrate. Okay, so what is happening, the incident light must traverse the full thickness of that substrate before it is getting reflected back. So there is a kind of there's a shift between the reflected images away from the pixel area. So this basically shifts the reflected image beams away from the pixel area the incoming beams are entering from. So you basically see a parallax. So here you can clearly see the two distinct dark contributions in reflection mode for an activated pixel. So a dark image is this one. This is the dark image, basically A prime B prime. So it is generated at the top polarizer, and you see a shadow image which is C prime D prime, okay, is basically generated at the bottom polarizer. Okay, so these are shifted apart, so the shadow appears to trail below the dark image. Okay, so why it gets worsened with smaller pixels? So when the pixel size shrinks or the pitch shrinks, you are basically going for high resolution, and in that case the fixed substrate thickness induced shift will become a larger fraction of the pixel size. So how to fix this problem? You can basically move this bottom polarizer and the transreflector into the cell. Okay, so practically that is enabled by in-cell polarizer technology, which is based on thin crystal films which are grown from the aqueous lytropic liquid crystal of supramolecules. So that can basically allow it. Okay, so one more quick explanation of this two image effect that you are seeing here. So you can consider a single activated pixel which is viewed obliquely, okay, So one incoming ray path is AB, okay, enters and it is blocked by the top polarizer and generating a dark contribution at positions A prime, B prime that you see here, okay. But a second that is a geometrically distinct incoming ray path C prime D prime, that also enters at a different point, travels down the activated twisted nematic layer, and it can come down and get absorbed by the bottom polarizer, okay. Now what it does, it can basically generate a second absorption event that happens at this bottom polarizer, okay, and physically below the thick substrate. So this second dark region is considered as this shadow region, okay, that is appearing here. So that is basically, that appears to be shifted away from the first dark image, that is A prime B prime. Now let us look into the transreflective multimode twisted nematic LCDs, okay. So the second twisted nematic or super twisted nematic weakness beyond parallax is that in the reflection mode light, it basically interacts with the polarizer adjacent structure more than the T modes single pass backlight. So this extra interaction of the reflection mode basically lowers the reflectance relative to the T modes transmittance, because the reflection mode has to go through it twice, right? So what is a solution for that? Okay, so the solution of the Sharp Corporation proposed by Molson and Tillin was that why don't you move the transreflector inside the cell, okay, so that basically fixes the parallax, and also it will reduce the color leakage for by pairing polarizer with a half wave and a quarter wave film set, okay. So you can see there are lambda by 2 and lambda by 4 sets are being used here. So this is the internal transreflector, okay, that is placed within the cell, and this half wave, that's 15 degree plus the quarter wave 75 degree, this film pair is placed on each side of this mixed mode twisted nematic cell, okay, between two parallel polarizers here. You see these two polarizers are not crossed, they are the parallel ones. So what is the role of this film pair that we are seeing? That each half wave and quarter wave plus the adjacent linear polarizer combination, that basically acts as a broadband circular polarizer across the visible range. So it can give you good dark state at every wavelength simultaneously, okay. Now let us examine the role of this mixed mode twisted nematic layer at V equals 0. So it equivalent to a quarter wave film, this behavior with the two broadband circular polarizer, okay, is shown here. So you can see when the voltage is not there in the reflection mode, what is happening, the light is basically rotated 90 degree through the top films and the MTN layer, and it reflects internally. So it can basically rotate it back to the original polarization on the return pass, and it can exit the top polarizer. So you basically get a bright mode. Now for the transmission mode, the light is coming from the backlight, and when the voltage is not applied, because of that half wave, quarter wave and the polarizer, the backlight basically becomes circularly polarized one after passing through this both film pairs and the MTN layer. So only partial transmittance through the polarizer is possible, okay, since a circularly polarized beam cannot fully pass through a linear polarizer, okay. So that is basically, but you can get light out of it, so you are basically getting bright modes in both R mode and reflection mode when the voltage is off. Now when you consider the voltage to be on, you can get basically dark state for both modes. How it works? The bulk liquid crystal director basically tilt up, so the two boundary layers compensate each other and light emerges rotated 90 degree relative to the exit polarizer's axis in each case, hence the light gets blocked. So you are basically getting dark state. So this is the voltage dependent transmittance and reflection of a transreflective MTN LCD, where the phi is 90 degree and d delta n is considered to be 240 nanometer, and you see that both modes operate in normally white case. Now if you compare this MTN with only TN, that is the multi-mode mixed mode twistor pneumatic with twistor pneumatic, you can see that for the reflection mode, okay, for one circular polarizer it stays at 100%, okay, until the twist angle exceeds something around 73 degree, and then it declines, okay. That means the transreflective MTN design gives excellent reflectance across its whole practical twist angle range. Now if you compare this with the T mode with the circular polarizers on both sides, that is basically the MTN case, this is the solid line. So you can see that the transmittance basically falls steadily as soon as the twist angle exceeds 0 degree, and it is regardless of the d delta n, and you can see at 90 degree it is the transmittance is only around 33%, okay. Now if you consider the same T mode without any circular polarizer, okay, what you see is basically a flat line at transmittance equals 1. That means your transmittance can reach 100% for any twist angle, okay, between 0 and 100 degree, and this is the conventional transmissive twisted pneumatic cell, what it can achieve, okay. So what is the key insight here is that the two broadband circular polarizer basically gave the mixed mode twisted pneumatic display a very dark and color uniform reflective state. However, if you consider these polarizers, they also absorb part of the transmitted light, so that will basically reduce the brightness of your T mode. Therefore, improving the dark state that you get in the R mode basically comes at a cost of the lower brightness in the transmission mode. So this is the fundamental limitation of the transreflective MTN structure. Now let us look into a method of how to remove the circular polarizer specifically for the transmissive light path, okay, and that is where this patterned retarder is getting into picture. So you can basically remove this by, so this part has got no retarder, but the reflective part has got patterned retarder, okay. So this is the core idea here. You can remove the circular polarizer specifically for the transmissive light, okay, by patterning the retarder film such that it appears only on top of the reflector region. So in the reflector region, what is happening, this patterned broadband phase retarder, which is basically the half plate plus quarter wave film wet coated, okay, and it operates in the MTN mode, so it allows you to reach that reflection mode transmittance what we have seen 2 slides back, right. However, if you see the transmission region, that operates like a simple twisted pneumatic cell without any polarizer, so you can get actually this feature which is 100% in the transmission mode, okay. So this the design DWN values that were used, these were from the Philips, okay. The transmission region TN mode DWN of 476 nanometer, that is basically the good steady condition. And the reflection MTN mode, this part had a DWN of 240 nanometer. So the cell gap layer is different. So here you are using twisted nematic liquid crystal layer, here you are using MTN liquid crystal layer, that is the mixed mode liquid crystal layer. So the patterned retarder works well. So this is how the voltage dependent transmittance and reflectance curves of the patterned retarder reflective MTN/TN LCD looks like. So you can see the voltage, the reflectance and the transmission curve overlap over the full voltage range, and they are very close to each other, so they give very good grayscale, okay, between this transmissive and reflective mode. Also, our design can provide high contrast, low power, low color dispersion, and a similar kind of electro-optical switching characteristics in both the regions. However, just to notice that the reflectance remains slightly lower than the transmittance, because 90-degree MTN region has the maximum normalized reflectance of around 88%, and on the other side you have 100% transmittance. So there is a bit of mismatch, right? So what is the drawback in this kind of assembly is that the oblique angle sensitivity is there. So the transmissive and the reflective regions, they occupy separate areas within each pixel. So at large viewing angle or incident angle, light may enter the wrong region, okay, and this may reduce the image quality when the display is basically viewed off axis. Second important thing is the difficult retarder alignment. So the broadband retarder must be patterned at the subpixel level. So it must also be aligned precisely within the reflective region only, and that basically increases the fabrication complexity and as well as the manufacturing cost. Okay. So you can see the transreflective mixed mode LCDs with dual rubbing MTN, okay, or the ECB, that is basically the electrically controlled birefringence mode. So what is the core idea? To generate genuinely different liquid crystal director orientation in the two subregions via different rubbing direction rather than patterning an extra optical layer, okay, without the retarder. So this is the schematic, okay. So you see there is this top substrate here, it is uniformly rubbed. However, the bottom substrate has two different rubbing directions. So one is like 75-degree twist for the reflective region where MTN will be there, and 0-degree twist, or it is homogeneous for the transmission region, or that is basically the ECB, electrically controlled birefringence. Remaining parts, polarizer 1 and the half wave quarter wave plate, that remains same. At the bottom also you have something similar, you have this substrate and then you have the half wave quarter wave plate plus the same polarizer again, okay. Now the single cell gap works for both here, because here you see instead of having two different cell gaps, you are maintaining the same cell gap here. So the D delta N requirement for 75-degree MTN and ECB happens to be close enough so that you can actually go for one uniform cell gap that can serve the two regions, transmittive and the reflective regions. So in that case, no dual cell gap fabrication step is needed. Now when you measure the performance and the design verification for this one, you will see that the both transmissive and reflective regions here use the same optical retardation. So D delta N comes out to be around 278 nanometer, and with this shared cell gap, both this T mode and T is the darker one, T mode and the reflection mode, they reach nearly their maximum light efficiency at approximately the same shared voltage, okay, and this also gives, and they try to follow each other, so you get good voltage response as well as grayscale matching between the two modes. And the selected D delta N value is basically a compromise between the requirements of the two liquid crystal modes, and here the compromise is slightly biased towards the reflection mode, as you can see. Okay, and that is why the transmission mode efficiency is slightly lower in this case than this one. Now there are some cost associated with this method as well. Dual rubbing is a complex method and it's costlier step than a uniform single direction rubbing. Second thing is the desalination line formation. So a defect line basically tends to form at the border between two differently rubbed regions. So that will basically lower the brightness and the contrast of that region. So there will be some local disturbance. So there are different strategies people have shown. So this is the dual cell gap concept and the transreflective ECB LCDs. Okay, so different strategies have been adapted from the mixed mode designs. So another strategy is to keep the liquid crystal alignment identical everywhere, so the rubbing angle does not change. So you just have a single rubbing direction, and for both the regions in the ECB mode, only the physical cell gap is varied by changing the length. So this is the cell gap for the transmission region, this is the cell gap for the reflective region. Okay, so why it works? The same halving principle introduced in the vertical alignment cell, we have seen that, and the thinner reflective region, because here you have to, the light has to go through the path twice. Okay, so it's basically having the double optical pass as compared to the backplane's single optical pass. Okay, so that can be introduced here. The remaining layers of polarizer and half wave and quarter wave film, those things remain exactly same. So what is the advantage that you get here is that no dual rubbing process is required, so no desalination line defect. So here both the regions have identical and simple fabrication steps, and this was pioneered by the Sharp Corporation. So the dual cell gap design rule is that the D reflection will be half of the D transmission. So if you are using D transmission DTWN as 336 nanometer, for the reflection you use half of it. Okay, and with that what you have achieved, that your transmission and the reflection mode both can achieve the maximum transmission reflectance simultaneously. They are perfectly matching and they are best for grayscale matching of any design that is covered in this module. However, there will be still some drawbacks, because here a boundary alignment distortion region, okay, that needs the black matrix coverage, then a slower transmission region response time because you have a thicker gap. Okay, so the response time will be different, and a narrow transmission mode viewing angle, okay, that is there because you are sharing the sides, and so your viewing angle needs to be very close to the normal. However, the last one, this viewing angle problem can be solved by substituting a biaxial film for the quarter wave film. So what is the final verdict here is that because its fabrication process is fully compatible with the existing high volume LCD lines, this dual cell gap transreflective ECB LCDs are now the mainstream commercial approach for this transreflective LCD products. There are other cell gap variants as well, like dual cell gap transreflective vertical alignment LCD, or then you have transreflective other like fringe field switching and the other ones, those are also there. Now let us look into the concept of single cell gap transreflective LCDs, where you will be trying to maintain a uniform cell gap throughout the entire pixel. So you are not having a stepped gap geometry. So in this case the reflection and the transmission mode, okay, dynamic switching responses, the time required will remain same. So that is directly avoiding that dual cell gaps response time mismatch problem. Okay, so you have to think of a design where these issues are taken care of. So one representative design can be using an image enhanced reflector. Okay, so the backlight here is reflected by an IR toward the reflection area, okay, giving the transmitted beam also a similar optical path to the ambient beam, okay, just like the reflection mode. So you are basically creating a reflection longer path for the transmitted beam. So you are basically having the same color saturation in both modes. However, you are adding an extra cost of this IR alignment complexity, which you have briefly seen in the previous slides. Now, previous lecture actually we have seen this IR, right? So the designs already covered that also belong to this category are like transreflective twisted nematic or super twisted nematic, transreflective MTN, okay, and all the dual rubbing mixed mode designs. For all of them, if you use a image enhanced reflector, all can keep one cell gap and instead vary the liquid crystal alignment spatially. However, there is some fundamental limitation to this. For any single cell gap design that does not also use a genuinely mixed liquid crystal module, ambient lights double pass and backlight single pass through the same gap cannot both be optimally compensated. Okay, so this is exactly why single cell gap mixed mode LCDs that requires dual rubbing have not been commercialized yet. So there is also a issue with the color filter thickness, and it comes from the fact that the reflected light, which is basically the ambient light, that passes through the color filter twice, okay, while you will see the transmitted, that is the backlight beam, that crosses through the color filter only once. Okay, just imagine the color, the IR image that we have seen in the previous slides. Okay, so using that you can think of it. Now this causes an inherent color imbalance between the reflection mode and the transmission mode. So what can be fixed? First fix can be a multi-thickness color filter, that is MTCF, okay, which is incorporated by the Sharp Corporation again. So they make the color filter roughly thick, half as thick in the reflection region as compared to the transmission region, so that whenever there is a double pass of the ambient beam and there is a single pass of the backlight beam in the transmission mode, okay, they will experience nearly the identical total spectral absorption. The second fix could be a pinhole type color filter, which is again introduced by Sharp Corporation. So here you will keep the color filter thickness same for both the regions, but punch small holes in the reflection region so that the ambient light passes the color filter entirely. However, some drawback is that the ambient spectrum mixes RGB primaries, so that basically will narrow the color spectrum range or the gamut. The third fix could be the scattering field color filter. So you can fill the reflection region color filter with some scattering material, and it will reduce the effective optical thickness to about half, just like a multi-thickness color filter, and it will let a simple flat metal reflector to be used, since the filler itself will now provide the diffusion functions. So if you compare the performance in terms of the image brightness and the viewing angle, you will see that there are brightness losses, because the RGB color filters are inherently have different attenuation levels. So the openings on metal transreflectors, aluminum reflectivity is only found to be around 92%. So each transreflected area is dedicated to either reflection or transmission, so that is basically capping the backlight utilization. So what is the fix for this brightness problem? You can use micro tube array. So these are basically funnel shaped micro tube structure below the transmission pixel area that can concentrate more backlight through the transmission openings, and they have actually shown 81% improvement in the backlight utilization without changing the transmission and reflection area ratio. Okay. The second important point is the transmission mode viewing angle. So this is limited primarily by the liquid crystal director's tilt angle, and it can be improved by substantially using a biaxial film instead of a plain quarter wave film, which we have already discussed briefly in the dual cell gap ECB LCD section. For the reflection mode viewing angle, which is limited primarily by the surface reflection or the specular reflection, you can introduce bumpy reflector that can diffuse light to different angles. So that will basically widen the viewing cone and it can steer it away from the specular glare. So what finally we understand for the modeling is that because incident and exit angles at the bumpy reflector generally differ, so optical modeling of the R mode viewing angle must account for this kind of asymmetric geometry rather than simply assuming a simple mirror-like reflection. So with that we conclude this lecture. If you have got any query, drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.